Good afternoon, everybody. We're from the group 3. We're going to talk about a gain and phase margins and relative stability analysis. Now, the group should consist of me, Papinfit, and should be the other one, but is Ansel, but God knows where he is. Okay. Now, I want to talk a bit of the theory of the gain and phase margins. Now, do you know what is margin? Difference, right?
Yeah.
So,
Between something and something, difference between one number and another number.
yeah, the difference or the value or an interval between something and something. Well, here the size of margin is an extra of something that we can use before something becomes no longer desirable. Like we have a page margin. We don't write over the page margin because after that you will write on the desk itself, right? So margin can be like the page margin itself, a margin of error like this, or here we will talk about the gain and the phase margin. We will talk about in detail later on. I want to talk about more. Do you understand margin, right? Okay, good enough. Now, say we have a general system right here, an open loop system. What makes the system to be unstable? We know that the system will be unstable if we have a pole on the right half plane, right, on the imaginary axis and the real axis. And what if we could change the transfer function in the block diagram into a closed loop? What open loop characteristic make the closed loop unstable? Now, if we change the closed loop, we will have the similar open loop like this, right? Typical from open loop to closed loop equation. And say we want this unstable to be like this, right? We know that the unstable system will actually propagate more and more and more, becoming more and more unstable. Now, say thus this is going to infinity, where the system will be going to infinity, right? What makes this system to be infinity? Simply, we want the bottom right to be 0, right? Correct? Thus, we can make the bottom one, the poles, to be 0. Thus, we have to be unstable, the GS must be -1, the gain itself. The gain itself must be -1. Thus, that is the criteria to be unstable for an open loop system or closed loop system like that. Any question? Okay. If not, then if we have this criteria to be the system to be -1, the gain, we can transform it into the Bode plot using the criteria to be that we know that this is -1, then the magnitude is 1 itself. We change it into decibels. We have the crossover point of the magnitude to be 0 dB. And then the phase itself, we know that the gain, because it's -1, it just flips the input upside down. It's like if we put 1, the output will be -1. Do you agree? Okay. Maybe you will see the more clear picture after I show some examples. Now, phase margin itself, like we know that margin is something of extra before it becomes undesirable in the output itself, right? Thus, phase margin is how much phase do we have from the 180 degree phase or the gain crossover frequency. So the phase margin itself, say we have a phase right here. Okay, we know that to the point of the crossover in 180. Thus, where is the phase, the gain margin itself? Yes.
Is it like that's what the gain margin is?
Yes, that's where the gain margin is. But sorry, the phase margin is where the magnitude crossover 0, right?
Okay.
And then we see how much phase do we have from the 180 point. Do you get it?
Yeah. Very good.
Yeah. Thus, the gain margin will be the opposite. Is how much phase do we have at the crossover point, where the phase itself from the 180, from the equation itself is actually the gain at the crossover point minus 180, thus it will be plus 180. If it's the value is more than 0, then it's a stable system. Any question? Probably till now.
So the gain margin, sorry, the phase margin
Yes.
is that distance, right?
Yes. The distance at so we
Yeah, I know where you get. So is the value positive? Does the value depend when it's going up or going down?
yeah. Well, from the equation, yes.
Okay, so if it's down, it's negative.
Yes.
You can see that in the question.
Wait.
In that given example, the system is unstable because the phase margin is negative.
Yes.
Oh, okay.
Unstable happens when like it passes over the margin. So like from here to here is stable, but like once it gets to here, then it's considered unstable. Same thing with the gain margin. Up to here is okay, but like up to here is okay, but like up from here to the end is like not okay. You can see more into this in the presentation. You guys will understand.
Now the gain margin itself is self-explanatory, where it's just the opposite of the phase margin itself. So the gain margin is right here, where the equation you could use a 0 minus the decibel at the crossover frequency of the phase. So to get the gain margin, you look at the phase. To get the phase margin, you look at the gain. Okay. So the equation is just general like this. Typically, we see instability using the phase itself.
Phase margin.
Yes. Margin in the magnitude on the gain isn't really self-explanatory because it could be stable because the instability actually happens in the phase itself. Okay?
Below that,
Well, it's still a margin where we can use it for something. Let's say we have a phase margin right here where we cannot really change the phase itself. Some say we can just change the gain margin. It's one way or another.
Feel like when you design a controller, sometimes you can change 0 or gain or the phase. So maybe it's kind of nice if you know what is the margin. In the case when you need to change the phase margin, just change.
I will talk.
You cannot change gain. Then
Well, I will talk about compensators later on because it's a little bit more interesting to see why the gain margin and the phase margin actually useful in using the Bode plot itself. Okay. Now let's try an example right here. What do you think the phase or gain margin right here?
payment is that and phase margin is
The phase margin is low.
Well, I'm going to make it a little bit easier. We know that we can use the phase margin. We can find the phase margin when we see it's crossing the 0 right here, right? And then where is it lies? Well, around 150-ish. So 150 plus negative 150 plus 180, we have around 30 degree. So technically, it's a stable system.
Okay, yeah.
More than 0. More than 0. So it's a stable system. But what about the phase margin? What do you think about the phase margin?
Phase margin is all the way right.
Correct. If we can see right here, it doesn't actually touch the 180 line. Thus, we can say the gain margin is infinity because it doesn't even cross the 180 degree line. Now, I want to talk a bit about the compensator. This is how you can manipulate. Let's say we have a phase that right here. This is literally the criterion itself, right? We can actually manipulate for the gain. So we can shift the gain by actually just manipulating the gain itself. That is the most easiest way. we're shifting it by up or down, where we can change the intersection point left or right.
If the gain also.
Yes, we can shift the gain crossover by actually just manipulating the gain itself. Where on the phase itself is a little bit more complicated. We need a lead or a lag compensator, where we actually shift the crossover on the 180, so it doesn't intersect where it want to be. So typically, that's why the lead lag compensator are actually really useful. Say we want the system to be more stable, we can just shift it using a lead compensator. Or we want it to be a little bit more faster, we can use a lag compensator. Like that. I think that's all from me. Now to
Okay, before we get into more examples, I would like to just review on how to plot a Bode plot. It's like, I know this is a bit different from you guys. Some of you guys use tables, or even like the previous group, they use the plot calculations, right? But I personally use this table from, I forget what textbook is called. But this helps me to make the Bode plot. And I'm just gonna review it through quickly, so just so you can get the idea on how to plot it. For example, we have this transfer function, 1 per s plus 1. Very simple, right? What I will do is that I will split this into two main functions, I would say. The first one will be, I didn't write. The first one will be 1 per s. The second one will be 1 per s plus 1. The reason why I split into these two is because, again, I go back to my table. From my table, I can see a relationship where 1 over JW, or in this case s, 1 per s to the power of n, will yield me a magnitude plot of like this and a phase degree of like this. Same thing with this one over here. It looks a bit crazy. 1 per 1 plus JW slash P per n. But in reality, JW is just S and P is just a coefficient. In this case, it's going to be 1 per 1 here plus JW is S and our P is 1. So we have no P. P is just 1. And N is, we don't have any power, right? So it's 1, right? That's why I'm able to look at this and I know that N is 1 and P is 1. And I refer to the table again. Okay, if N is 1 and P is 1, what is my magnitude? A plot. Magnitude says it's going to start descending when it starts at P. My P is 1. You're going to start descending at P with a slope of minus 20 N decibel per decade. What is my N? My N is 1. So there you go. I am able to find my magnitude graph. Same thing with my phase degree. What's that? This is what it looks like when I plot it in MATLAB. Okay. And I think you can just go through this. Yeah. So like it's 20 degrees. The graph. But this is the main part that I think is the main aspect of this presentation. To find the gain margin. Basically, to find gain margin is very simple. What you need to do is okay. Yeah. No, it's fine. Okay, to find gain margin, very simple. Trace the point of 180 degrees on the phase diagram. On the phase diagram to the magnitude diagram. Trace a point of 180 degrees of the phase diagram to the magnitude diagram. Next slide. Okay, so you have this plot, right, from MATLAB. Magnitude, phase. To find gain margin, look at the phase. Find 180. Where's 180? So right, 180, right? You trace a line all the way. And if you see closely, it's very hard to see, but this is actually an asymptote. So what does it tell us? Infinity, exactly. Right? It does not, our line never touches the margin. Never touches 180. There. Never touches. So it tells us that gain margin is infinity. Okay, next one. How about phase margin? Simple, it's not just the opposite. Trace the point of 0 decibel on the magnitude graph to the phase diagram.
Hold on. Go back to the previous slide. So what does it mean when gain margin is infinity?
It means that it's able to be stable no matter how much gain you put.
No matter how much you gain. Okay.
Yeah.
Thing like that.
That's it. And phase margin. trace the point of 0 dB on the magnitude. It's going to be the opposite, yeah? On the magnitude graph onto the phase diagram. So then we want a phase margin, right? We look at the magnitude graph, we trace from 0, the green line, and we hit this point where the line touches our graph. We'll be able to see a point over here. We just click on MATLAB. They give us system, the frequency, and magnitude. Then what we do next is that we're gonna trace a plot from here to the phase diagram, and we get this point. This point here is the crucial part. This point here will tell us what is the phase margin. Our phase margin will be over here, negative 128. But we want this to be under 180. We want it to be always in 180. Say that your phase margin is like 200 minus 200. You want to plus 180. If it's plus 200, you want to minus 180. What you want to do here, the phase is always to be within the scope of 180. So in this case, it's 128, right? And if you plus 180, it will still be a value of below 180. So that's what we want. That's what we get. 51.8. So our phase margin will be 51.8 at 0.786 radian per second. Next step. This is what I mean. 0.786 radian per second. Next step. This value is what we call the gain crossover frequency. So if 5.18 is our phase margin, 0.786 is our gain frequency. Kind of confusing, right? We're talking about phase margin, but then we're getting gain crossover frequency. The reason why we get this is because we are referring our phase margin based on the magnitude graph. That's how you remember it. We are basing our phase margin on the magnitude graph. So we are using the gain crossover frequency. Next slide. Some more problems. Next slide. Next slide. This is a problem I get from the textbook that we use for CSD. Another one. Transfer function of k per s plus 1, s plus 5. Assume that k is 10. MATLAB code. Skip. This is our graph. Alright, now I want you guys to practice. Tell me what is the... I forget what I put here. I think gain first. Let me see. You guys, look away. Look. I forget what I asked. Oh yeah, I asked for gain margin. Alright, I want gain margin. Tell me what is the gain margin for this graph. Oh, bro. No. Tell me the steps. All right. Negative 180 from phase. Right. Slide. Yeah. Boom. And boom. Okay. Point. All right. What does this tell us? What does this value tell us?
The gain margin is 5
minus 9.5 plus
This is gain, right? So gain we don't. Yeah, gain. So like if phase you want it to be always within 180, right? But for gain you want to be the opposite sign. So if you get negative 9.5 here, your gain margin will be the positive 9.5. Yeah, it works that way. I don't know how, but like it works that way. Yes. And similarly, like the previous question, you are able to find what is called the phase crossover frequency. Phase, yeah? Because we are based on the phase diagram. So, this is what I mean. So 2.23 is our phase crossover frequency.
Why do you say you do right?
Yeah, I think like I haven't practiced enough. I haven't studied enough.
Okay, let's go back again to the definition of gain margin. The gain margin is
the margin between the
I like the phase margin. How much an area you have left before you are out of the plot.
Yeah, this is phase.
Also, gain margin is
How much
limits of gain for the system.
how much gain you can increase before you are passing zero. That's the gain margin. Fine. So it's 0 minus your gain and it's 0 minus that. So like you have your gain minus 9. 0 minus 9 you get plus. Your gain margin.
Oh yeah, this one.
Yeah,
Yeah. So gain is always like 0 minus what you get from the graph. Yeah. Next slide.
So,
Oh yeah, now it's gain. Now it's the phase diagram.
It's margin.
Phase margin. Sorry, phase margin.
So,
Yeah.
how can you tell this is stable or not? From just looking at this.
It's equal from yeah, it's different from under under 150 something is above 150. I think it's 150.
50?
And this one, right?
No, I mean, yeah, the
Yeah.
phase.
You mean this one?
The phase of
Yeah.
frequency. So, just like 4, trace it to 0 where it intersects. Trace it down again. Have that. You know the phase is 155 minus 150.
You always want it to be within 0 to 180, right?
Delta, right? Delta.
Yes, the delta. Hey, delta. Yeah, sure, delta. It's like,
And then the phase margin we only have.
so it's gonna be 155 plus 180. 25. And then our frequency is 1.23 radian. And tell me what is this? What is this? No. Gain or phase? Why gain?
Because we trace it from gain.
Yes, because we trace from gain. It's like,
What if I want the system to place the gain right here? It's stable. I place a gain right here.
say like your gain is gonna be, how much is this? Let's say it's negative 40. Your system
No,
is
I'm sorry. What if the input that I want to be is at this frequency? Is it stable? No, right? No, it's not stable. It's over 180, right? Well, how do you make it stable?
I'm gonna sit there. We add another block.
Alright, we can do two ways. Either we shift the gain or just make the phase.
Oh, so phase is always like front back, right?
Yeah.
But if gain is gonna be up down.
Yeah, this line moves up or down. This line will slide.
Alright.
But the crossover point is not.
The stability that we have. So, kalau kita dapat itu like it doesn't mean that like or
10 to 1 resistor.
yeah, it doesn't mean that that's that and that is good.
From the criterion, why is it
The
stable?
criteria is getting the imaginary part. The stability measure
So it's going to be Nico's, right?
our correlative stability that is dependent on the frequency. How we get the gain one, this one, right now. That's how we get.
So sir, for stability, we just see at phase and gain, right?
Yeah, we only see the phase and gain. They are both positive. If one of them is negative, then so that's the goal.
Okay.
But this is relative. Yeah, so you can adjust like relative stability is different from stability that we learn right something. How to use criteria. That's different. The relative stability. it's right know how to communicate anything does the provides the good thing design.
For gain, ideally infinite, and for fish it's also infinite. So that means like no matter how much you gain input, it will be stable.
And
But
possible for solar system. This system that of practice of was clear to value from the and for the gain margin, this will get more than 6 million. Get what's that? Infinity. Gain margin infinity, you show it as well.
yes, on a first
The first.
What about base margin?
okay, hold on. I remove it.
That's
Yeah, sure.
Let's say square. 1. It like this, I forgot.
But the idea will be like it's gonna be as input. So like it will never touch 0.
Well, ideally like this.
Yeah, I think like this. I think it's an example. So like the 0 is like the asymptote. It will never touch 0. So this is an example of base margin. It's infinite.
that's not
Oh, that's not close to right?
It doesn't have a pole.
Oh, what was this? What?
1 over s plus 1. No, it's yeah, you can use that also. Hold on. 1 over s plus. Yeah.
yeah, it's for them.
Oh. So it's not infinity then? So it goes below 0.
Mm.
What about the gain margin?
Non-existent.
Yeah, so infinite is non-existent 0.
Yeah. It needs to be an asymptotic hit to 180, I believe. How about this?
That is
S touches
yes.
Oh, no, it has a game margin because it has a crossover at 0.
Yeah.
What do you guys think? Well, of course lah. Well, in theory, it should be second order system because it needs to be 180, but we can shift. The problem is it needs to be asymptotic to 0 at least, or 180, both.
I don't think.
Yeah, I don't think it's possible.
Yeah.
But like for it to be infinite, it has to like go up, right? Go up and then asymptote at something.
No, just from your example that value is of whatever it's value of the angle at the possible. Like, how do you get infinite at
That has to be 0.
no. Your answer.
Ah. No, it's impossible, sir. Because the formula is 0 minus.
This is the margin minus 180.
No. The fixed margin can be infinite, but gain margin cannot be infinite. Yeah. It's either 0 or not, sir. Huh? Gain margin cannot be infinite, sir.
Oh, yeah, it's the other way around. Gain margin.
Oh yeah, gain margin.
Phase margin.
What?
Base margin is up.
Yeah.
Base margin. For the cost of the system, it's the third cost.
But is there a case where phase margin is like the reason for that is because of gain, right? Because gain is 0 minus whatever we get.
Yeah. So get the cost of the base margin.
Phase margin. So we look at that horizon. 0. Like this thing is 0. That's also
This
yeah, the margin is infinite because it has not reached 90.
So.
Do we learn this?
yeah.
Is there some more practice problems? Let's see if you guys can do it. It's a bit more interesting. This time there's gonna be both gain and fee. As you can see. Okay, this one. Another problem. It's a bit more complex now. Your transfer function is 20 s plus 1 over s plus 5 s squared plus 2s plus 10. So this is s to the power of 4. And I already showed the answer. But this is what it looks like. And this is something where you can get both phase margin and gain margin. Going back to our explanation before, find the gain margin, you have to look at the phase diagram. Draw a line from 180 to up there. The magnitude, negative 9.94. Swap the signs, become positive 9.14, and we get a frequency of 4.01 radians second. Tell me what is this? What is this? Tell us.
That's the base possible.
What's the reason for this?
That's where the
Yeah, because you're basing gain margin based on phase diagram. So remember, yeah, gain margin is based on phase diagram. So your frequency crossover it will be phase because you're using from phase. Right? Now for the phase margin. The thing again at 0. Then we draw a line. Phase margin. We want the phase margin to always be within the scope of 0 to 180. That's why I add 180 here, 104. And then the 4 at 0.455. This is simple, right? Now this is next slide. And now this is maybe just the last slide, I guess. Just a little bit trivia. I just want you guys to be aware that even though like you have gain margin, you have phase margin, you must try to look at the broader picture where it might be stable at first. The margin is very good, right? Let's try to draw the phase margin example. Right? Phase margin, so from 0, we draw a line.
Okay.
I've done right. So we got phase margin of maybe approximately negative 100, right? Yeah, alright, negative 100 phase margin. But you have to minus 90. So that's 80. That's 80 degrees phase margin, right? So, okay, that's pretty good. We want, like what's the say we want to be 30 to 60. But after you look at the bigger picture, you see a huge drop over here. This is dangerous. From last time you get 80 degrees phase margin, now it's almost close to, almost close to 0. And that is dangerous. You don't want that. So just make sure that every time you plot the diagram, look at the big picture. Don't just look at your scope. Try to expand the scope. And this is another one. What happened like if just now, and this is what happened if we just changed the poles, right? These two are the same transfer function, except look at the poles. This is plus 6s, the one is plus 3s. Right? Plus 6s is the blue line, plus 3s is the orange line. And yeah, you can see the phase and the gain margin is different. I would say that
Probably the more bigger picture is that be careful when designing a controller, because even though if you add a compensator like a lead lag, sometimes if we don't see the bigger picture, we can make the system unstable just by changing one number, only one.
Now let's look at the phase diagram. It's so different. You only just change by plus 3s, right? Just it's so different. So even the tiniest change of poles or of zeros, it can affect your system, your phase margin and gain margin of your system. That's the point.
We talk about relative stability. It's much lighter topic than the last two topics that we have discussed. From these two research to conversions with two closed wall, there is graph on the imaginary and real axis. Which one do you think is the more stable system, A or B? A. Why A?
Because it's far more located far from the real axis.
Right. Okay, so as we know, the closer to the zero, the closer the pole to the zero, the more unstable it is, and at the less stable it is.
Still stable.
Yeah, stable. Sorry. Or yeah, the stable is when it crosses to the right hand plane. So to grab the to understand the closest of the pole to the zero, we will use something called is the conformal mapping. It's where you map the closest poles in the real axis and imaginary axis, and then you plug it into the requisite pole of requisite plot of the transfer function to get the the distance from the outmost real part to the -1, which when if you remember in a near-case plot, -1 is the origin of the plot, where -1 why -1 because the transfer function the characteristic equation of the near-case plot is 1 plus GHS.
Karena
Okay.
That should be good.
Yeah, I guess. Tapi Sir, but in the textbook, right after gain margin and base margin, it is ini Sir.
Yeah, that is definitely coming from the
Okay.
yeah, which says that for stability
Ya, tadi kan has been mentioned tadi bersama Sir.
yeah, that's it. From the whole plot.
Then we'll. Anyways, long story short, in an axis spot, generally, the closer the GS or GJ omega to the -1 plus 0 imaginary point, the larger the maximum overshoot in the step transition response, and it will take a longer time to time out. That's basically it sih for the understanding. I will throw in some questions ya abis ini. Next example. Which again do you think is the more the less stable the right one? Okay, now we'll see ya. We'll see. You are correct. Yay! And the last line is just another abbreviation of it. So, this is the more clear example of the last slide, where you can see that on the left side it is less closer to the -1 from the right side. And honestly, that's it for our presentation. Sih. Thank you guys.
Any questions for they already have to get
Okay, I ask.
Yes.
Like, basement in margin, you always take the delta, right?
You can say that.
Which means it is always positive.
No,
Oh,
For gain.
not always.
Go to your giving one. When you
The
just show
beninging.
when you just show the level for the face active.
Which one?
The one with the this one. Gain margin, it's 0 minus the whatever the value of
yeah, minus 20 log.
Yes.
minus 20 log. So if the base crossover is behind the gain crossover, that means the gain crossover, the gain margin is negative. Am I making sense?
If what? If what?
If the
There.
yeah,
This is negative.
if the phase crossover frequency
Phase crossover frequency.
is behind
High.
gain crossover
Uh-huh.
frequency, gain is negative.
Gain margin is negative.
Yeah, gain margin is negative.
Because it goes down.
Yeah, we know because it's 0 minus.
Zero
Yeah,
minus
minus
whatever
Yeah.
this is.
Okay. It's again.
Margin.
Save.
Nggak usah ganti. Base margin? Well,
Yeah.
rumusnya ini. The
So-
equation is this.
So you take
Take
the same that, so you
the angle of
Base, middle of the base.
Where it
Cross over.
Crossover frequency minus 180.
minus
Plus 180.
plus
180.
That's the part.
So in here we have how much ya? One, let's say 200 lah ya. 200
minus 200.
yang I mean minus 200 plus 180
Minus 20.
minus 20. Like both are negative. That means
Negative.
yeah, that means
It's
unstable.
stable, right? Because
Yeah.
kurang dari 0.
That's it.
Setiap aja lah ya. Gambar dulu.
Null min. Yeah.
It,
Null mean whatever the dB it is.
ya,
Yeah.
magnitude is 8 S.
That's it. What else?
Basically, ya.
It's basically it.
You guys want to special
Yeah, lah. Yeah, you can calculate it, but it's difficult. So you have a transfer function, make it 0, and do the rest.
So to find the margin, we make the transfer function, put in one end, and we see.
Yeah,
The most easiest way is that you can do mathematical way.
That's right.
Oh!
Yay.
Gas.
Let's pick a
That is
Yeah, that one over S times S plus 1. Yeah.
Yeah.
What? And this one is equal, right?
Yes.
Get the answer. Then we go.
Okay, the answer is
first step is get the gain protocol.
Oh, make the answer to 0. No,
make gain to 0. I think it is first.
one.
gain equal to 1 in dB 0.
This is equal to 1. Change S with J omega.
Here we go.
Omega then equals to 1. J omega.
No, on the left of the
Gain crossover.
It's J omega. So it's
like
1s.
times T omega.
Oh, my bad.
Then you make the absolute and
Yeah.
Absolutely.
Here.
I have no idea.
Oh. Absolute.
one.
Okay.
Find the magnitude.
Yeah. Multiply J omega with
One over.
plus
1 over plus.
Oh yeah. Yeah.
Oh, now we have
Ah.
1 over W
square of
square square.
Omega square.
J.
plus
Omega.
square of 4.
Ya kan part of the imaginary times imaginary square plus D Omega square plus
J omega.
Square J omega lah.
Omega doang.
Omega
Omega doang.
Omega doang. Magnitude-nya Omega.
Negative omega square because
You do it.
is negative 1.
Ya.
Because J is imaginary number.
Gak usah pakai itu lagi ya.
Pasti
Gak sih?
Kan udah magnitude.
Udah
Apa aja kamu? Berpikir sih. Jangan gua.
1.
Ya, itu apa? Omega square minus omega square.
Omega square.
Omega square minus omega.
Plus
Apa sih?
omega square plus omega dong.
Omega square.
Omega square
Plus
plus omega. Ya dong.
Oh enggak lah.
Apa dong?
Kan omega square.
You know what?
divide by omega square plus 1.
Square root.
Omega square plus 1.
Oh. Apa bro?
Oh iya betul.
Speak one by one.
Iya omega. Iya omega keluar and then.
Gue bikin akar dulu yang gede nih.
No, I think you're correct already. Continue.
Say it one by one.
Kita root of apa? Omega square.
Omega square plus 1.
First, you multiply this with this first. So you write down 1 equal to square root of
Square root
omega 4 plus omega square.
Ya.
And then we square both left hand side.
Ya.
1 equal to plus omega square. Okay, now you take out the omega square. 1 equal to omega square times
plus
plus 1.
one.
And now you get the omega square.
Oke.
Omega square equals to 1 over
1 over omega square.
Omega square plus 1.
Oh yeah.
Oh yeah, mix the one goes to the other side.
1 goes to the other side.
Zero equal to
Iya. Ulang. Berarti gini.
So I think we start
Omega
with
4 plus omega square minus 1 equals to 0. Nah, ya betul.
just move to one outside.
Omega 4 plus omega square minus 1.
yeah, plus minus.
Ya plus minus. And then
Root omega square.
omega square.
Ini bro.
Bukan itu.
Minus 1.
Hah?
Omega square minus 1 plus omega square plus 1.
Ah,
Jadi itu jawabannya.
omega square plus 1. Kali omega square 1. Tadi kita punya omega square sama dengan minus 1.
Stop correct.
Ayo.
Stop correct.
Betul lah. Enggak bro. Omega 4 plus omega square plus omega square plus 1.
Makanya jadi hilang bro.
Oh iya. Gitu. Harus pakai rumus kecap bro.
I got this, bro. Negative 0.786 and positive 0.086.
Ya.
Terus
Yeah, the omega square is 0.618.
Oh yeah.
That's the answer. Omega square is 0.618.
No, okay. Okay, 0.786, sir. Okay, 0.786.
Think omega square.
Omega square. You root it.
Not minus.
Don't buy this. Is
There's two values here. Oh,
Just erase it while you add the plus. No.
0.786.
That's right or wrong?
Yeah, correct.
We have three values then. Oh.
Next look. Tulis nggak tahu?
No.
Nggak tulis. Oke.
so it has to be somewhere around here.
No. This is 1,
This is
2, 3, 4,
Yeah.
5,
0.7.
6, 7. Around here.
Dan gua makan itu tadi kan.
Iya.
Iya.
Kayaknya ini bukan
Beda graf ya?
beda gerak.
No, it's not.
I think it's my graph. Do the next slide.
Just make a new plot. Aduh. S plus plot. Dikurung-kurung, jangan lupa.
Oh, yeah.
There we go. This is zero. Ya, magnet lah, ya.
I'm good.
Aman aja.
Yeah, okay.
Cocok.
That's good.
Udah.
Close.
Yeah, that's close enough. That's close enough. 0.786. Yeah,
How
it's
we get
close.
the base margin?
Now that I don't know.
Once you get the omega in that case,
Sabar. Wait.
you plug in the omega into your original.
Okay.
Okay. Don't know how to do it.
Angle is it like tan?
Yeah. Tan inverse. So,
Why am I doing it again?
okay, we will use this.
Okay.
Yeah, we'll use this one. Okay. So you put there g of j omega is equal to this. Yeah, g of j omega
Nih, dia kok gede.
is equal to this. Minus omega square plus minus omega square. Rewrite that. That's okay. Is equal to 1 plus j omega. Okay, now you plug in this omega here. Minus of that. Now it's different, you know. Minus of that you square it of minus of that base squared is different. You square first and then square first and then you minus.
Bentar.
Yeah. And then 0.6. Okay. Yeah. Now the angle of this is equal to.
For this one, I got
Is equal to 0 minus
0 minus
tan inverse of the 0.786
0.786.
divided by this value but minus
Sorry. This value with minus.
minus of 786.
negative 0.1.
Eventually, more than cars.
Oh, okay.
Okay, what's the value now?
On the bottom one is
What's the tan inverse value?
Oh, ini kemarin ada di
Of course it's there.
kemarin ada.
it's in radians.
Ya,
0.9 radius.
In radian in degree. Put it in the degree of course. Subtract paling. What's the value?
Your calculator, hold on.
Have to change the degree version.
No one can compute it.
Anyone complete that?
It says negative 51.8.
degrees.
Yes.
0 minus.
The tan here.
So 0 minus 51.8 degrees. Kan? Jadi,
1 plus 51. That's all.
Oh, it's not a calculation mistake.
Oh, double-click.
Mana? Kurungnya mana? Oh, di dua. Degree.
Yeah, right. Keyword.
One.
Face margin.
Not face margin. The face well, the frequency. And that's the
Oh, sorry, sorry.
Lebih 387. Oh, what is this? 100.
Non negative 100.
Let's see.
Plus 50, plus 90.
Dapat sir. It's not 0 minus something, but 180.
oh yeah.
Oh yeah, 180. Yes, yes, yes.
Oke banget, benar juga.
What the value of tan equals 0?
Negative 51.3. Yeah, kan masa?
I think it has to like. I think 180 like depends. It's plus or minus. Right?
No, from
What was it?
kriterianya kan?
This one is gonna be 200.
No. Hold on.
Iya. Saya review still ada aja juga.
Minus 180. Minus 180 plus 1.8. We are looking for the phase angle first.
This is Q1.
Sorry kak.
Yeah, the angle coming from the top can be minus 180, can be 0, can be 180. But we put it there, all these are zero. Correct. Put minus sign in here. Minus sign. Then what do we get? That's the phase.
1, 2.
Minus 1 to 8. Yeah. Minus. So when we use minus, it will be the same with the graph.
Iya, sama.
So the plot is, we are using, when it is 0, we have minus 180. Then inverse 0, put it minus 180. Yeah. So basically when you are looking for the angle, let's say you have your g omega, the a plus g omega here, and then f c plus j times t. So the angle the tan inverse g over a minus tan inverse g over c. So because the top part is 1, the value will be either 0, 180 or minus 180.
Because the top part is 1.
Yeah, the top part is 1. The real part is 1, imaginary part is 1.
Oh, I see. Yeah.
So whether you put 0 here, 180 or minus 180, they are the same. Actually.
Okay. Thank you, sir.
What do you do?
Okay. So that is our presentation about phase margins, terus apa lagi? Gain margins, and then about the wrong relative stability. Thank you for listening to us. Bye bye.